So I'm going to go through the review questions from PCB272 that I set for week 3, and these can be found on Blackboard. So question 1 is about diagnostic radiography, and a question about when photoelectric absorption occurs the most. Okay, so which one of these 4 materials has the largest likelihood or most significant likelihood for photoelectric absorption to occur? Okay, well the answer is bone, and that's because this has the highest effective atomic number. Okay, so bone is made up of a number of constituent atoms and elements, and its average effective atomic number is more significant than tissue and fat, and certainly obviously air, or at least air is not a very dense material, so that's why we don't get a lot of photoelectric absorption in it. Okay, so the answer here is C in this case for bone. Okay, moving on to question 2. Attenuation of an X-ray beam within matter is not affected by, so just be careful, this is a negative question. Okay, this is just to make you think a little bit about it. So the attenuation of the X-ray beam is not affected by Compton scatter. Well, that's a scattering situation. Okay, so there's no, it will remove X-rays from a beam. Okay, transmission of photoelectric absorption, well, this will also contribute to the attenuation. An atomic number, okay, and electron density, these do affect the amount of attenuation that we get. So transmission, okay, so this question was really about making sure you understand the difference between transmission and attenuation. So the answer is transmission. Okay, so these are the X-rays that pass through without interacting in our material. Okay, all the others are going to affect, are related to attenuation. Question 3. The mass attenuation coefficient increases with electron density. Okay, so actually as we increase the energy, actually the mass attenuation coefficient decreases, and the other's temperature of the material doesn't influence it, and the mass attenuation coefficient actually increases with increasing mass number or atomic number. Okay, so the answer here is electron density. Okay, question 4, the linear attenuation coefficient. Okay, so this defines the probability of absorption or scattering taking place. So we have an attenuation coefficient for Compton scattering, we have an attenuation coefficient for photoelectric absorption, and we have an attenuation coefficient for pair production. Okay, so in this case it's answer B. So just be aware actually that in your question set I may have randomized the answers, the order of the answers, so B might not be the correct answer for your question set. Question 5. Which interaction process does not take place in the range of energies of a diagnostic beam? Okay. Well, the answer here is pair production. Okay, A in this case, and the reason for this, remember, is that pair production is the absorption of the X-ray by the nucleus, and that energy that's absorbed goes into creating 2 new particles, an electron and its antimatter particle, the positron, and therefore we are creating 2 new masses. And Einstein told us that the mass and energy are equivalent. I'm sure you've all heard of E equals mc squared. Okay, energy is proportional to mass, and therefore we need a threshold of at least the masses of the proton, the positron and the electron. And that equals, in energy, 2 times 511 keV, so that equals just about 1024 kilo electron volts, or 1.2 MeV. Okay. If the photon, the X-ray, has an energy higher than that 1.02 MeV, then the result is that it's given to these electrons and positrons as kinetic energy as they move away from the atom. Question 6. The probability of photoelectric absorption occurring. Is most likely when it's equal to or just above the ionization energy. So my question set here is D. Okay. And this is because the atom has to actually be able to absorb the energy. Okay, so the X-ray is going to interact with the electron, the atom, and therefore that electron needs to have a binding energy that's or ionization energy, as I've called it in the question, that's close to the energy of the incident X-ray. Okay, any excess X-ray energy is going to be greater than is going to be given to the photoelectron as kinetic energy. Okay, so as it moves away. Question 7. Decrease. Okay, but I think in the notes I showed you a graph. The Compton scattering, the photoelectric absorption decreases more quickly than the instance of Compton scattering. Okay, so they both decrease with energy, with increasing photon energy, but what we find is that what I was saying was that, at higher radiotherapy energies we get more Compton scattering. So although it's still decreasing with energy, we get more Compton scattering at higher energies than we do at photoelectric absorption. So just have a look at the notes of the plots I showed you of the probabilities of Compton and photoelectric as a function of energy, and you'll see that. So the answer here was actually B, sorry. Mass attenuation coefficient, another question about this. So the mass attenuation coefficient is the linear attenuation coefficient divided by the physical density. Okay, so if we know the physical density and linear attenuation coefficient, we can work out the mass attenuation coefficient. The probability of a Compton interaction. Question 9. This is proportional to the electron density, or it's proportional to the electron density. Okay. Sorry, I didn't put the answer in on this one. Yeah, so it depends on the density of the electrons. The more electrons there are per unit volume, the more likely it is we're going to get Compton interaction. Okay, there's a little or no dependence on atomic number. Okay, and question 10, which I think is the final one in this set. In the photoelectric absorption process, the vacancy from the photoelectron is filled by an electron. So this is about what happens after photoelectric absorption. Okay, so remember the photoelectric absorption, the atom absorbs the X-ray. Some of that energy is given to ionizing, so removing an electron, and that leaves a vacancy in one of the shells. And so the atom is what we call an excited state. So what normally happens is an electron from an outer orbital drops into the inner orbital where the vacancy is, and the result is a characteristic X-ray. I mean, I don't mention characteristic X-rays here, but that's what happened. Okay, what we need, so it's the vacancy from the photoelectron is filled by an electron from the orbital shell further out. Okay. Okay, so there were also a set of revision questions that went over pretty much everything we've done in the first 3 weeks. I'll just quickly go through these as well. So just get them up on my... Alright, I've got 2 screens running here. Okay. So the first question is just testing that we understand what about the Bohr model of the atom. Okay, and this tells us really, this is that we have a positive nucleus, okay, surrounded by electrons in well-defined shells or energy levels. Okay, so we've got a dense positive nucleus made up of protons and neutrons, and that just answered the next question actually, surrounded by electrons in well-defined energy levels or orbitals. Question 2, the nucleus of an atom contains which of the following? Well, the answer is protons and neutrons, okay, positively charged neutrons and neutral neutrons, and they both have a very similar mass. Question 3, the electron shell closest to the nucleus is termed what? Well, we call this the K shell. Okay. The next question, the electron shell closest to the nucleus, second closest, sorry, so the next one out is termed the L shell. Okay, and then the next one would be M, and then the next one N. And each of these shells, remember, is only allowed a certain number of electrons. There's a maximum number of electrons for each shell. And for the K shell, that first innermost shell, the maximum number of electrons is 2. Okay, so we can only have 2 electrons in that K shell. Which electron shell has the highest binding energy? Well, the answer here is again K. So the electrons which are closest to the nucleus have a binding energy, have the highest binding energy. They're the most tightly bound. And I think this is reasonably intuitive to understand. If we have a negatively charged mass and then a positively charged nucleus, then the closer the electron is to the nucleus, the higher that binding is going to be. Okay, so the K shell is always going to have the highest binding energy. Question 7, the electron binding energy. How do we define this? Okay. So it's the energy, remember all the electrons are bound to the atom and it's in a stable state. And to remove an electron requires energy. Okay, it takes some energy to remove that electron from this, because of the binding force that it experiences when it's in the atom, in the orbital. Okay, so we define the electron binding energy as the energy required to remove an electron from the atom. So when an electron is removed from an atom, okay, so when this occurs, and the atom is said to be ionized. Okay. An ion pair, so what happens after ionization? What are we left with? Well, we've removed a negatively charged electron. Okay, and we had previously had a neutral atom. So if we remove a negative charge, we're going to be left with a negative electron and a positively charged atom or ion. Okay, so the answer here is a positive ion and an electron. So the element boron 11 has an atomic number of, well, if you need to look up in the periodic table, okay, you would find that boron has an atomic number, Z number, of 5. Okay. And therefore, moving on to the next question, the element of boron, 11. Okay, so if it has an atomic number of 5, then this tells us we have 5 protons. And if the mass number is 11, it means we have 5 neutrons and protons, and therefore the number of neutrons is the difference. So it's 11 minus 5, which is 6. Question 12, the mass number of an atom. Well, what is this? I've just said this actually. It's the number of protons and neutrons in the nucleus. Okay. And the atomic number, probably should maybe swap this order of these questions around a bit. This is the atomic number of an atom is the number of protons, and it's also the number of electrons. Remember, in a neutral atom, the negative electron charges and the positive proton charges balance, and therefore the atomic number is equal to the number of protons and also equal to the number of electrons. So if we have, in the case of boron, we have 5 protons, atomic number 5, it also has 5 electrons. Question 14. Question 14. The periodic table of the elements lists the elements in order of increasing. Well, they increase in order of atomic number. Okay, if you look at the periodic table of the elements, you'll see the top left-hand corner is hydrogen, and then on the next one along on that top row is helium, which is right actually on the other side of the periodic table. Then we drop back down to second row far left, and we would see, just trying to think what it is, beryllium I think. Okay. And so on. So the atomic number is increasing. So as we can move left to right, the atomic number increases, and then we drop down a row at the end of that particular row. So question 15, what are isotopes? Well, they're atoms with the same atomic number but different mass numbers. So they have the same Z, atomic number, but different mass numbers. Okay, so in the case of boron 11, we could also maybe have an isotope of boron 10 or boron 12. They would still be boron. Those would be defined as isotopes of boron. Okay, but they have the same atomic number, 5, but different mass numbers, so different numbers of neutrons. So the half-life of a radioisotope, it's the time required for half of the original atoms to have decayed or be transformed, okay, of the parent. So it's the time it takes for the half of the original atoms to decayed or transformed. So, it's an exponential. If we look at that, the activity or the number of atoms of a radioactive isotope and stable isotope, we see it falls off exponentially, and we hear a lot about exponentials recently in terms of the infection rate of the coronavirus. That's also exponential. But in the case of the number of infections, that's obviously an exponential increase, whereas radioactive decay is a decrease. Okay, and one parameter you'll hear discussed or mentioned quite a lot in terms of the coronavirus and how the infections are increasing is something known as the doubling time. So this is the time it takes for the number of infections to increase by a factor 2. And this is the same parameter as the half-life for a radioactive decay process. Okay, so just remember that exponentials can describe decay processes, and also increase processes where the numbers increase. Okay, so half-lives and doubling times are a way to parameterize those exponential processes. So next time you see a coronavirus curve showing the increase in the number of infections, just remember that. Question 17. Electromagnetic radiation. Well, the only electromagnetic radiation there is X-rays. Okay. Beta particles, alpha particles, and neutrons are obviously not electromagnetic radiations. They are ionizing radiations, but not electromagnetic radiations. And the last question, ionizing radiation consists of particulate radiation and electromagnetic radiation. Okay, so includes all these. Okay, that was a very quick run through of the answers of those questions. If you have any questions about any of them, please don't hesitate to contact me.